Welcome. Today we solve valid k unique Subarrays 1. This is a hard problem, but we will go very slowly from 0. For every query range, we ask, does that subarray have exactly k distinct numbers, and does every number appear an even number of times? By the end, you will understand the rules, the examples, and Mohs algorithm. What are we given? An array nums, an integer k, the exact number of distinct values we need, and many queries, each arranged from left to right. For each query, we return true or false. So the output is a Boolean list with one answer per query. A subarray is valid only if both rules pass. Rule 1. It contains exactly k distinct numbers. Rule 2. Every number's frequency is even. 2, 4, 6, and so on. Example, 1, 2, 2, 1 with k equals 2 has two distinct values, and each appears twice. That is valid. If either rule fails, the answer is false. 4 words to remember. Distinct means how many different values. Frequency means how many times a value appears. Even means 2, 4, 6, divisible by 2. Odd means 1, 3, 5. Subarray means a contiguous slice from left to right. Keep these words in mind for every example. Example 1 setup. Nums is 1, 2, 2, 1. K equals 2. Queries are 0 to 1, 0 to 3, and 1 to 2. The expected output is false, true, false. We will check each query carefully. Query 0 covers indexes 0 to 1, subarray 1, 2. Distinct set is 1 and 2, size 2, which equals k. Good so far. But frequencies are 1 each, both odd. Even frequency rule fails, so this query is false. Exact k is not enough if counts are odd. Query 1 covers indexes 0 to 3. Subarray 1, 2, 2, 1. Distinct size is 2 equals k. Frequency of 1 is 2, even. Frequency of 2 is 2, even. Both rules pass. Answer true. This is a perfect valid k unique subarray. Query 2 covers indexes 1 to 2. Subarray 2, 2. Frequency of 2 is 2, which is even. But distinct size is only 1, not equal to k equals 2. So it is false. Even counts cannot save a wrong distinct count. Example 2. Nums is 3, 3, 3, and k equals 1. Query 1 to 2 gives 3, 3, 1 distinct, frequency 2 even true. Query 0 to 2 gives 3, 3, 3, 1 distinct, frequency 3 odd false. Output true, false. Same value with odd length means odd frequency. Why brute force fails? Both n and the number of queries can be 100,000. If you scan every range from scratch, time becomes about n times q, which is too slow. We need a smarter offline method. That method is Mohs algorithm. Mohs algorithm idea, explained simply. We answer queries offline. First, sort the queries into blocks so the left and right borders move less. Keep one current window. When we go to the next query, we add or remove only the elements that changed. Then we read our maintained statistics. Think of it as a sliding window that jumps between queries. What do we maintain in the window? First, frequency of each value. Second, distinct. How many values have frequency greater than 0? Third, odd. How many values currently have an odd frequency? The range is valid if and only if distinct equals k and odd equals 0. Odd equals 0 means every frequency is even. Add one element x into the window. If its old frequency was 0, increase distinct by 1. If old frequency was even, the new frequency becomes odd, so increase odd by 1. If old frequency was odd, the new frequency becomes even, so decrease odd by 1. Then add 1 to frequency. That is the expand step. Remove one element x from the window. Decrease its frequency by 1. The parity flips again, so update odd the opposite way of add. If frequency becomes 0, decrease distinct by 1. Remove is the shrink step. Keep add and remove perfectly mirrored, so odd stays correct. Sort queries into blocks. Choose block size about square root of n. Queries in the same block share similar left indexes. Inside a block, sort by right index. This classic Moh ordering makes the window travel less total distance, which makes the algorithm fast enough. To move the window to a query left comma right, use for while loops. While current right is too small, add on the right. While current right is too big, remove on the right. While current left is too small, remove on the left. While current left is too big, add on the left. Then set the answer to whether distinct equals k and odd equals 0. Algorithm steps. 1. Store each query with its original index. 2. Sort by Mo order. 3. Start with an empty window. 4. For each sorted query, move the window to that range. 5. Record true only if distinct equals k and odd equals 0. 6. Write answers back into the original query order. Time is about n plus q times square root of n. Here is the add and remove code idea. In add, if frequency is 0, bump distinct. Then flip odd based on current parity, then increase frequency. In remove, decrease frequency first, flip odd from the new parity, and if frequency hits 0, drop distinct. These two helpers are the heart of Mo's for this problem. Here is the Mo main loop. Build query tuples with left, right, and original index. Sort them by block of left, then by right. Start current left at 0 and current right at -1, meaning empty. For each query, align the window with the 4 while loops, then store whether distinct equals k and odd equals 0. For example 1, this returns false, true, false. Tiny Mo dry run on 1221 with k equals 2. Start empty. Move to query 0 to 3 by adding all 4 elements, distinct 2, odd 0, true. Then move toward query 0 to 1 by removing the last 2 elements, left with 1 and 2, both odd false. We never rescanned from scratch. The window just moved. Code walkthrough. Sort queries in Mo order but remember original indexes. Use add and remove to maintain frequency, distinct, and odd. Align the window to each range. Write the Boolean into the original position. The pattern is maintain, move, red. Edge cases. Distinct can be correct while some frequency is odd, still false. All frequencies can be even while distinct is not k, still false. Constraints guarantee left is less than right, so length is at least 2. With many queries, you must use Mo, not naive scans. Track frequencies carefully for values up to 100,000. Key takeaways. Valid means exactly k distinct and all frequencies even. Even means counts like 2, 4, 6. Many range queries make brute force too slow. Mo's algorithm answers offline with one moving window. Maintain frequency, distinct, and odd count. Valid when distinct equals k and odd equals 0. Sort queries by blocks to reduce movement. Restore answers to the original order. That is valid k unique Subarrays 1, explained from 0.